Hello, everybody, and thank you very much for joining us today with a very warm welcome to you for the forthcoming presentation on controlling waterborne pathogens in the greenhouse through the role of oxidation by HPNow. Before we begin, I just want to ask that if you have any questions for the speakers, then please write them in the comment section, and I will endeavour to ask them your question at the end of the presentation during the Q&A time. Without further ado, let's introduce today's speakers. Firstly, we have Arnaud Verdiger, the co-founder and director of products at HPNow, where he spearheads innovative solutions in water treatment technology. With a PhD in physics from the Technical University of Denmark and advanced studies at Stanford University, Arnaud has established himself as a global authority on oxidation processes, particularly in the application of green hydrogen peroxide for water treatment. His pioneering work has garnered multiple prestigious awards, including a spot on the Forbes 30 Under 30 list and the Horizon Prize from the Royal Society of Chemistry. Our second speaker is Cord Nunez, the Sales Director of Agriculture in North America, HPNow, who has a background in agronomy and brings over 2 decades of agricultural experience in addressing the critical challenges facing the North American agricultural sector. Cord's career has spanned key roles at leading agtech companies, where he developed a national strategic strategy to support organizational growth. Cord specializes in tackling water scarcity and security, autonomy and sustainability issues. By applying best practices and effective methodologies, he contributes to advancing the agricultural industry's understanding of these pressing concerns. So, ladies and gentlemen, for this session, Arnaud and Cord will delve into the topic of on-site green oxidation and its role in creating a healthier and more productive growing space for your crops. By understanding how one can safeguard your crops, maximize greenhouse potential, and implement effective strategies for controlling waterborne pathogens. So, gentlemen, the floor is all yours. Thank you.
Thank you so much, Jonathan, for the introduction. So today, as Jonathan mentioned, we will be covering the topic of controlling waterborne pathogens in the greenhouse through oxidation. And this is our first webinar. We thought it would be interesting, based on conversations we have been having in different trade shows and with growers and different stakeholders in the horticulture industry, to do a session more educational and more in-depth on how oxidation can help growers get better crops. So in the session today, we'll be covering different aspects related to oxidation technologies in the greenhouse. First of all, we will be going through the threat of biofilm and waterborne pathogens in modern horticulture, understand how oxidation can work in the context of decreasing plant disease pressure, and evaluating different strategies to enhance biosecurity in the greenhouse. Finally, we will look at some real-life case studies, and we will, of course, leave ample time for questions and answers, which are very welcome in this session today. So in modern horticulture today, there is increasingly a water biosecurity threat. This comes because there is growing pressure on water resources. There is less high-quality water that is available for irrigation. And water used for irrigation today usually is coming from recycled loops or from deep wells and different sources that have a quality that is not as good as it used to be in the past. At the same time, there is an increasing trend in recirculating water to preserve this valuable resource. And this comes with some biosecurity challenges. The first thing that growers are aware of with the poor water quality is that this poor water quality tends to generate more biofilm in the irrigation system. This biofilm, for one, it causes the irrigation to be non-uniform by clogging drippers and by clogging different valves and growing everywhere in the irrigation system. And the biofilm is a breeding ground for pathogens, which thrive there. They reproduce in the biofilm, and they spread through the water to the plants. We have today lots of issues with pathogens such as Pythium, Phytophthora, Fusarium, tomato brown rugose, fruit virus, and many others that affect the plants, and they cause loss production and increased cost for growers. The formation of biofilm is a complex process with several different steps. It's enough to have a single particle of a bacteria or a fungi that adheres to a surface, for example, an irrigation pipe, and it reproduces there. As it grows more and more, biofilm matures in this slimy structure that is green-brown in color that I think most growers are familiar with. And it forms bigger and bigger colonies. Then these colonies, they release spores where the biofilm then disperses and it reaches other points of the whole irrigation system or the plants. This comes with two negative consequences. For one, this leads to non-uniform irrigation, clogged drippers, clogged valves, and biofilm present in growing trays and different growing areas. And for two, the biofilm releases pathogens, which cause a higher disease pressure to the crop. If nothing is done to treat the biofilm, this will cause more and more problems over time. And in traditional horticulture, there were different ways to sort of be able to survive with biofilm. This is increasingly hard today because of the poorer water quality that growers have access to. And that's why oxidation plays such a vital role in securing a healthy water supply for the crops. What oxidation can achieve is it can oxidize all the biofilm and clean all the drippers and irrigation system. As it does that, it will also remove pathogens as well. It's important that oxidation does that without posing a danger to plants. And it's also important here that oxidation doesn't leave behind any unwanted residues after use that could sort of backfire and have a negative effect on the crop. And eventually, a good oxidation strategy will result in a strong positive economic impact for growers. There are several strategies for pathogen and biofilm control. But first, let's look a bit deeper into what oxidation is and understand a bit better the role it plays in the context of modern horticulture. So oxidation from a chemical point of view, it happens when the oxidation state of a molecule or atom is increased or an electron is lost. In the context of irrigation water, oxidation will break down organic molecules. This could include, for example, bacteria, virus, and different pathogens. Oxidation is provoked by molecules that are named oxidants, and there are many different oxidants available. Different oxidants have different reactivity and different oxidation potentials. But essentially, what we want an oxidant to achieve is to break down organic molecules. Here in the graph below, we can see an example of an organic carbon chain. And when we come in with an oxidant, what we want to achieve is to break apart this organic molecule, and this will render a bacteria or a virus inactive. Now, how to do that? So there are different oxidants available, as I mentioned before. Here on the graph to the right, we can see the different options that we have. And we can see here a term which is called oxidation potential, which represents how reactive a given oxidant is. The higher the value for the oxidation potential, the more reactivity a given oxidant will have. and the more reactivity, the less stable an oxidant will be. So if we start at this list from the top, we have here the OH radical, which has a very high oxidation potential, almost coming at 3. And having such a high number, this means that basically pretty much any chemical bond that this OH radical sees, it will break it apart. It's very strong, but it's also very unstable OH radical, so it can only survive for less than microseconds in the water. The list we have ozone, which is a well-known oxidant. So very reactive, but not very effective. If we go lower, we find here hydrogen peroxide towards the middle. It chlorine. We also find oxygen here as well. Oxygen is an important. When we look at oxygen, a molecule that is widely available in the air, and most subs have been exposed to oxygen before entering the irrigation system. What this means is that solutions that are based for oxidation are not effective in achieving oxidation aims, simply because there is so much oxygen in the air that has already done as much work here. So any solution that is aiming at increasing oxygen levels in water, that being through aeration or nanobubbles and etc., will not be able to reach the oxidation potential that other stronger solutions can, and it will not be as effective in these regards. And finally, towards the bottom of the list, we find hypochlorous acid and sodium hypochlorite. These are materials that are well known to most of us. They are not very reactive, and they are, as such, not very efficient at dealing with biofilm, but they are highly toxic at the same time. If we stop for a moment and try to think what the ideal oxidant would be in the context of horticulture, we would want something that is effective throughout the whole irrigation system, not only at the point of contact, but down to the last dripper or the last tray. We want to have an oxidation effect to be able to remove that biofilm and the pathogens throughout the whole system. We would like our oxidant to be safe to use, both for plants. We don't want the plants to be affected by toxicity from the oxidant, and we also don't want humans to face occupational hazards because of the nature of the oxidants. And finally, we want oxidants that don't leave any byproducts after use. This is very important when water is being recirculated. We don't want any byproducts from oxidation circulating in the water and accumulating in the whole irrigation system and the root zone. We will see later how this is a parameter that is very important to take into account as well. We have today different oxidation options available. Here there are some examples. So we have UV, chlorine, ozone, stabilized peroxide, and on-site peroxide generation that are highlighted here. Let me go a bit more in depth into the different aspects here. So starting with UV. UV is a light-based technology where high energy light inactivates virus and bacteria. As a light technology, UV is very good at the point of contact. However, it does require water that has a good transparency for the light to reach the water. UV is efficient at dealing with pathogens at the point of contact, but it will not have an effect in the whole irrigation system since it doesn't leave any residue oxidation in the water. Moving on to the right, we have chlorine. Chlorine is very well known as a traditional oxidizer. It's a toxic substance that while it will have some effect on biofilm and it will be able to remove some pathogens, it will always leave byproducts after use. We're talking about different salts and different compounds that are, in the context of horticulture, are not desired for the crop. Then in the middle, we have ozone. Ozone is a gas that needs to be manufactured on site, very unstable, very hard to properly dissolve in the water, and very reactive. So it's very efficient at removing pathogens at the point of contact, but it will have limited impact on biofilms. And then moving on towards the right, we have stabilized peroxide. This is peroxide that has been manufactured at a chemical plant. And in order to minimize losses during transport, because it's after all a reactive substance, a stabilizer has been added into peroxide. These stabilizers are usually heavy metals like silver or chelating agents. Industrial peroxide comes at a high concentration. This means that it can pose a danger both to humans that need to handle the peroxide in terms of occupational safety, for one, and for two, any overdosing can wreak havoc on the crops as well. So it's a substance that requires special care and special safety precautions as well. And finally, the stabilizers will always end up in the water and could have some negative consequences there. And finally, towards the right of the list, we have on-site peroxide generation. This is a new technology where you are combining water and electricity to generate a very reactive and very pure form of hydrogen peroxide that is made at the point of use, and it doesn't need to be transported. And it has a high efficacy not only at the point of contact, but also through the whole irrigation system. So when we're comparing available oxidation methods against the different parameters we're looking at before, if we're looking at, for example, on the first row here, solutions that have an oxidation effect through the whole irrigation system, here we need to exclude, for example, UV or ozone, which are effective at the point of contact, but they don't have the ability to reach beyond the point of contact. Solutions like chlorine, stabilized peroxide, or on-site peroxide, they can reach down to the last dripper in an irrigation system, and they provide this effect throughout the whole system. The next aspect here is the safe to use aspect. So occupational safety for humans or not reaching toxic levels for plants. Here, UV and on-site peroxide systems stand out because they are very safe to use and there is no danger to overdose the solution. If we look at solutions like ozone, chlorine, or stabilized peroxide, they all come with different dangers of either overdosing or occupational safety that is important to be aware of. And finally, when we look at the no byproducts after use, again, the UV and the on-site peroxide system, they stand out in this category because they don't leave behind any traces. And in the case of on-site peroxide, it will even leave behind dissolved oxygen, which is a positive nutrient for the root zone of the crop. If we look at other solutions, ozone, for example, it will leave behind byproducts from its use. Chlorine will always leave behind salinity as well. And Stabilized peroxide will leave behind stabilizers in the form of heavy metals or chelating agents that can also have a negative impact on the crop. This is what we can see from a more theory and a more lab-based perspective. Now my colleague Cor will bring a more agronomical perspective based on real-life case studies that we have been looking at with green on-site oxidation.
Great. Thank you, Arnau. Yeah, so like Arnau was referring to, it's great when we talk about all these different solutions and how they are, what their efficacy is of the solutions in a lab setting. But I like to look at it in a more practical sense and how we actually see it in use, in practice, in these controlled environment or out in actual practice in the field. The GoGen, or the green oxidation generator, it does control pathogens in the water system and at a much more higher efficacy than you would see in traditional peroxides or ozone in this case study. In this case study, they were using ozone prior to switching to the green oxidant, and they were experiencing losses from pythium in their system in the summer months, upwards of 20%. After switching to the GoGen, it was reduced, the mortality down to 1% losses in summer months. As you can see here, there's a significant visibility in the crop and how it looked prior to and after the GoGen was applied. So this is due to better crop uniformity, but it also the growers stated that they were able to get healthier plants and up to 10 days shorter in their growth cycle to get it to retail. This is mainly attributed to the increased oxygen levels in the water, but boosting the root zone and just making sure that the biofilm was completely clear throughout the system. As referred to earlier with that Arnau said, ozone has the ability to kill pathogens very effectively, but only at the point of contact. So as we're recirculating water, as in this case, the water was being recirculated, treated with the ozone, but there was no efficacy past that point. So downstream effects were not seen there. So biofilm was able to accumulate within the system, harboring these pathogens, and then during the summer months, they were able to spike. This is a organic blueberry crop in Almeria, Spain. This case study really goes to show the uniformity in the irrigation system that can really take effect with the GoGen. Because it's an organic fertigation being applied through the emitters, they tend to clog a lot more. The biofilm builds up, but not just that, the organic matter from the fertigation can also clog up the emitters. If you look at the left side of the picture, you see without the GoGen, it's not as thick or robust of a crop. And on the right, after the GoGen was applied, you're able to see a more vigorous plant growth and much thicker. This is due to one, the irrigation system. When an irrigation system is put in, usually you see about 95-97% efficiency within the irrigation system. Common practices in the field, what we see here in California especially, is we'll see about 75% on average drop in distribution uniformity. So clogged emitters, due to biofilm or organic matter, which then decreases the ability to get the plants the nutrients they need through the irrigation system. This also should note that we were able to notice a big increase in the organic matter found within the soil. And this is just due to the hydrogen peroxide, the ultra pure, being able to break down the organic matter fertigation, the fertigation being delivered in the fertigation system, and being able to make it more readily uptakeable by the crop. The grower also did see some increases in other areas, which is notably just due to delivering the organic matter and the water to all throughout the irrigation system. Now, this is in a vertical farm where the green oxidant was applied. This is notable because we can see that it can control pathogens, and in this case, coliform, which is very detrimental to leafy greens. In this case, lettuce production, where we saw a count of upwards of 1,500. And then after the GoGen was applied, we see the count was dropped down below that 500 mark, which is non-detrimental to plants and also to the food safety aspect of it. This also included better crop uniformity and predictability throughout the system by eliminating the biofilm in the system, and also increased oxygen levels and boosted the root zone. You can visibly see after the GoGen, you saw much more fibrous, vigorous root growth, much more white, bright in color, and mainly due to the dissolved oxygen. Here you can see it doubled in count from 3 to 6. The GoGen has been applied in many different agricultural applications and throughout geographically from Japan all the way over to the United States and California. It is organic approved, OMRI listed, and CAAE in Europe. The product is been used on all sorts of plants, from ornamentals to tropicals and to herbs, berries, and vegetables. So the way the system is applied it's not a traditional in sense of where you would see normal industrial hydrogen peroxide used. Other products are used for treatments when they see issues within the system or when the plants are removed in between plantings. This system is made to be safe and autonomous and run in the background using only water, electricity, and air. It concentrates the oxygen, the ambient air, and takes the oxygen and puts it into the heart of the system, which is the electrochemical stack, takes normal tap water and filters it down to DI water, and under equal pressures and through electrolysis, it's able to produce an ultra pure solution of hydrogen peroxide. That's then put into a reservoir of the grower's choosing. This enables us to be able to dose at whatever rate is needed. So when we talk about different flow rates of the different operations, we're able to do it just by injecting from different dosing pumps or any available input that the system already has. And from there, it's delivered to the irrigation system. This is done through preventive maintenance is also based on cloud-based solution, and it's also able to measure the concentration of the hydrogen peroxide that is being produced, which leaves it completely autonomous and supply chain free because you're generating it on site. The solution is based at a very safe, low concentration of 1%, but that is still 10,000 ppm, which is much higher than in any application that you would see in an agronomic setting. You're going to look at probably injecting anywhere from 20 ppm for pathogen control and only 2 to 5 for biofilm. So it's still very, very strong, but it is very safe. You will not have any issues with safety on that aspect. So let's talk about that, the safety between and the efficacy between industrial peroxide and which is stabilized peroxide generally, and then you have your ultra pure peroxide. Because the ultra pure is generated on site, it's stable for up to 7 weeks in the proper container, as where stabilized peroxide comes from the factory, so it's stabilized with either chelating agents or silver, as Arnaud mentioned. This then makes it less active, and that's one of the reasons why we saw this case study and the zoospore count and being able to take in-field applications where the peroxide, the silver stabilized peroxide, very high grade silver stabilized peroxide, was being used in application where the zoospore count was upwards of almost 400 present in the irrigation system. And after switching from industrial peroxide that was silver stabilized to the ultra pure, the grower then was able to test and notice that the zoospores were down underneath that 5 mark, which is non-harmful to plants. The other thing to note is the buildup of stabilizers that can happen with these heavy metals and chelating agents. Especially when in a irrigation system that the water is being turned over and reused, those then can accumulate in the irrigation system, and the only way for them to get out is through the plants. And those chelating agents and heavy metals can be a plant inhibitor, so that the growth potential is just not there. This can then also lead to mortality being dropped by being able to cut the zoospores count down, as you can see in the bottom right hand corner. So ultra pure does not interfere with the root zone of crops, as where the stabilizers and additives from stabilized peroxide can become a plant inhibitor. This, in ultra pure does not lead to the buildup of stabilizers because it's not present. Where the buildup of stabilizers, to summarize, in an irrigation system, especially those that are being turned over and water being reused, it can become a plant inhibitor over time. So ultra pure maintains its oxidizing potential and pathogen control ability. Basically, it's more effective because it is more active. And when you have a solution that's being stabilized, basically for storage and shipping, it becomes less active and has less oxidizing potential. The GoGen series that we have being offered by HPNow is in the cabinet size, standard server rack or a single door fridge. It's 1 to 3 kilograms per day in the one on the left, highlighted in blue. And then we have our larger series that can be run in sequence at 10 kilograms per unit and run in sequence. This can give you anywhere from 3 to 9 on the left hand side, or if you need more than that, 10 to 100 in the right hand side, where the components are just external, like the oxygen concentrator and the water components, the filtration and the RO unit.
So I just want to thank you very much, Arnaud and Cord, for your interesting insights that you've provided here today, enabling us to see the exciting work that you're doing in supporting growers through green oxidation and controlling waterborne pathogens for their farms. Also want to thank all the attendees as well for taking part wherever you are in the world. We hope this was insightful and knowledgeable for you too. If you also wanted to learn more about HPNow and how they're supporting and developing the sector, and as I've mentioned a couple of times, reach out to Arnaud and Cord, as well as visiting their website at hpnow.com and contacting them through the Contact Us section.